All right, so here we are for part 3 of section 4.3, hopefully the last part. My job is to find relative extrema of a given function on an interval. Okay, now that one's new. The last couple examples we had infinity, negative infinity to positive infinity. Now we're saying just a little tiny piece. All right, so let me see if I can figure this out. My job is to find relative extrema. That's high points and low points. So the process I'm going to go through is I'm going to find critical numbers, and then I'm going to find intervals of increasing and decreasing. And then I'm going to look at those critical numbers, and I'm going to check to the left and to the right and see whether it's increasing and then decreasing, which would mean we went up and then down and found a maximum, or whether it's decreasing and then increasing, which means we went down and then up and found a minimum, or whether it's increasing and we have a nothing, or decreasing and we have a nothing. Right? But either way, no matter what's happening here, our first step is we need to get a hold of these guys. We need to find our critical numbers, are critical values. First step in finding critical values is to get our derivative. So what is the derivative of 1/2 x minus sine x? That's going to be 1/2 minus cosine x. And now I'm going to look for my critical numbers. Critical numbers come in two flavors. They come in the does not exist and the equal to 0. I'll check doesn't exist first. Are there any values of x for which that derivative will not exist? Okay, I got a cosine x. Cosine works for all real numbers, so the limitation of 0 to 2 pi won't change that, so that's good. There's no division by 0. There's no roots of negative numbers. I don't think there are any of these. I think there are none of the critical numbers that come from the does not exist side of things. Are there any critical numbers where that first derivative is equal to 0? Well, let's do the math and figure it out. When is 1/2 minus cosine x equal to 0? Well, that's when cosine x is equal to 1/2. So that's when x is pi over 3. And remember, we're limiting ourselves to 0 to 2 pi. So one revolution of the unit circle. That's the first quadrant angle. But cosine's also positive down in the fourth quadrant. So what is the fourth quadrant angle that has the same reference angle as the first quadrant angle, pi over 3? That's going to be 2 pi minus pi over 3. So that's 6 pi over 3. So 5 pi over 3. All right, so I found two critical values. So now what I'm going to do is I'm going to check my intervals and see what's going on. Now if I draw my number line like I do, I know that I'm starting at 0 and stopping at 2 pi. I have a critical number at pi over 3, another critical number at 5 pi over 3. I know this is not to scale, but I'm just drawing it out so I can see what I'm looking at. And it looks like I have 3 intervals to test and 2 critical values there. First thing I'm going to do is I'm going to test interval number 1, which means I need a value between 0 and pi over 3. I can pick any number I want. I'm going to say let's make x be pi over 6. And then I'm going to find out what is the value of the derivative. That is, what is f prime of pi over 6. Right? F prime of pi over 6 is going to be 1/2 minus the cosine of pi over 6. Right? The cosine of pi over 6 is going to be, what is that going to be? Root 3 over 2, so 1/2 minus root 3 over 2. Well, same denominator. Root 3 is bigger than 1, so this is negative, so that's going to be less than 0. So that means that f prime of pi over 6, or more importantly, interval number 1, f prime is less than 0. Now I'll check the second interval. Interval number 2, I need a number from the second interval. I'm going to say, I don't know, what's between pi over 3 and 5 pi over 3? How about pi? That's an easy one. So what is f prime of pi? That's going to be 1/2 minus the cosine of pi. Cosine of pi, cosine of pi, cosine of pi. What is the cosine of pi? Let's see, the cosine of pi is -1, so I've got 1/2 minus a -1, so that's positive 1/2, which is greater than 0, so on the second interval, f prime is greater than 0. Now I'll check interval number 3, something between 5 pi over 3 and 2 pi. I'm going to choose to use, I don't know, how about 11 pi over 6. And so I'll find f prime of 11 pi over 6, which is going to be 1/2 minus the cosine of 11 pi over 6. So that's going to be 1/2 minus root 3 over 2, which is again going to be a negative value. So here we are less than 0. Right? So now what I need to do is I need to take what I just found and interpret it. So it looks to me, and help me out here, but just to make sure I'm understanding it, this is decreasing, this is increasing, and this is decreasing. So what's happening at these two critical values? Now I know that they exist for the original function. That is that these values are in the domain of the original function because my function has a polynomial piece and a sine, a trig piece, but both of those exist perfectly fine on the interval 0 to 2 pi. So I don't have any issues with them not being values in the domain of the function. So now I just need to interpret them. Pi over 3, to the left we're decreasing, to the right we're increasing, so we went down and we went up. So, whoops, I don't want that. It looks to me like that would mean that we have a minimum when x is equal to pi over 3. Using that same logic, 5 pi over 3, to the left we're increasing, to the right we're decreasing, so it looks like we have a maximum when x is 5 pi over 3. Right? But to talk about the extrema, we don't just need the x's, we need the y's, if you will, too. We need the f of x and the f of x. We need the y value at pi over 3. Right? So the y value at pi over 3 is simply going to be take that x value, put it into the original function, and see what you get. So we're going to get 1/2 times pi over 3 minus the sine of pi over 3. 1/2 times pi over 3 is going to be pi over 6 minus the sine of pi over 3. Sine of pi over 3 is root 3 over 2. And that really is about as good as I can do with that. Now I'm going to do the same thing down here to find my maximum. My maximum is going to be when x is 5 pi over 3, so that's going to be 1/2 times 5 pi over 3 minus the sine of 5 pi over 3. 1/2 times 5 pi over 3 is going to be 5 pi over 6 minus, let's see, the sine of 5 pi over 3. Sine of 5 pi over 3 is the same as the sine of pi over 3, but just in the fourth quadrant. So it's a root 3 over 2, but a negative root 3 over 2. So plus root 3 over 2. And that's about as good as it gets. So my minimum is the point pi over 3 for the x value, pi over 6 minus root 3 over 2 for the y value. My maximum is the point 5 pi over 6 plus root 3 over 2 for the y value, and 5 pi over 3 just for the x value. Now, I know that at least one person out there is saying, how come you're not checking the endpoints? What if there's a max or min at the endpoint? Endpoints aren't included. This is an open interval problem. So I don't have to check the endpoints. I only have to worry about the interior of the interval. Of course, if I'm the least bit worried that my math is incorrect at some point, I can always graph the original function, limit it to the interval 0 to 2 pi, and look for those mins and maxes that way too. Okay? All right. Another one of the same thing. Find the relative extrema of a problem. So I'm going to do the same thing I just did. Step 1, find my derivative. But I'm not a huge fan of how that's written. And wouldn't it be easier if it wasn't written so messy? I don't want to use the quotient rule. So can I rewrite this as x squared plus x to the negative 2 and work from there? And then when I take the derivative, I get 2x minus 2x to the negative 3 for my derivative. Okay? Now, if you prefer, we could rewrite that and call that 2x minus 2 over x cubed. And maybe that'll make finding those critical numbers easier. Okay? Critical numbers. I always start with the does not exist. Are there any critical numbers from the does not exist here? Well, it looks like we have one. It looks like when x is 0, we're going to get a critical number because we're going to try to divide by 0 in that second term right there. We're going to try to divide by 0 here, and we can't divide by 0, so we got a critical number from the doesn't exist side of the world. Now, that worries me because sometimes critical numbers from the doesn't exist end up being points that aren't in the domain of the function. And so they don't really truly end up being maximums or minimums. So just hold on to that in the back of your head, and we'll think about that later. Okay. What about the other kind of critical numbers? The critical numbers that come from setting the derivative equal to 0. Are there any values where this is equal to 0? And so I'll solve this algebraically. That's going to give me 2x is equal to 2 over x cubed. So that means 2x to the fourth is equal to 2. That means that x to the fourth is equal to 1. That means that x could be positive or negative 1. So it looks like we've got 3 critical numbers here. So I'm going to draw out my number line, place my critical numbers on the number line. That's going to give me 1, 2, 3, 4 intervals to test because I have 3 critical numbers, breaking that number line up into 4 pieces. Right? I'm going to test each one of them. I'm going to test interval number 1. For interval number 1, I'm going to pick x as negative 2. Sound good? What's the value of the derivative when x is negative 2? I'm going to use the blue version of the derivative. Let's see, that's going to be 2 times negative 2 minus 2 over negative 8. So that's just going to be plus a quarter. So negative 4 plus 1/4, that's less than 0. So over here, f prime is less than 0. Decreasing function. Interval number 2. I'm going to pick x to be, I don't have much choice here. How about a negative 1/2? Ugh. F prime of negative 1/2, 2 times negative 1/2 plus 2 divided by negative 1/2 cubed. 2 times negative 1/2 is negative 1. Negative 1/2 cubed is negative 1/8. 2 divided by negative 1/8 is going to be negative 16. So minus a negative 16 is going to be plus 16. So on that second interval, it looks like our derivative is greater than 0. Now I'll check my third interval. I'm going to use positive 1/2. So the value of the derivative at 1/2, well, that was an ugly 1/2 right there, is going to be 2 times 1/2 minus 2 divided by 1/2 cubed. 2 times 1/2 is 1, minus, that's 16 again, right? So that's negative. So on our third interval, f prime is less than 0. Fourth interval, I'm going to pick x to be, I don't know, how about 2? Sounds good to me. F prime of 2, 2 times 2 minus 2 divided by 2 cubed. 4 minus 2/8. 2/8 is 1/4. That's positive. Okay, now here's where if a mistake is made, it's going to be made. Okay, all right. What's happening at negative 1? Well, to the left, we're negative first derivative. To the right, we're positive first derivative. So that means we're decreasing left, increasing right. So I think we have a minimum at negative 1. Right? So what is f of negative 1? So that's going back up here, right, to the original function. F, not f prime. So let's see, that's going to be, whoops, still had the arrow thing turned on. That's going to be negative 1 to the fourth plus 1 over negative 1 squared. Negative 1 to the fourth is 1. 1 plus 1 is 2. 1 over 2 when it's all said and done. So we have a minimum at the point negative 1, 2. Right? All right. What's happening at 0? Well, to the left, we're positive first derivative. That means we're increasing. To the right, we're negative first derivative. So that means we're decreasing. So increasing, decreasing, you want to say this, right? You want to say you have a max at 0. But you don't. Because if you attempt to evaluate f of 0, you get this. It's undefined, right? Because the rule says you've got a max if it goes up and then down, but only if that critical number is in the domain of the original function, and this is not in the domain of the original function. So we do not have a maximum there. Okay? All right, last thing. We need to check what's happening at 1. To the left, our first derivative is negative, so we're decreasing. To the right, our first derivative is positive, so we're increasing. So I think we have down and then up. I think we have another minimum. At positive 1, I'm going to check. What is f of 1? That's 1 plus 1 over 1. That's 2. And we have a minimum of 1 comma 2. Now this is a wonky one, so I'm actually going to go look at the graph of this function and see what the graph of this thing looks like. So I come over here, go to Desmos, because that's the best thing I can find a graph. My function was f of x is equal to the quantity x raised to the 4th plus 1, and then divide that by x raised to the 2nd. And here's my graph. Okay, let me put that in projector mode. Here's my graph. What do you see? Well, I see that there's a minimum there. I see that there's a minimum there, but there is no maximum because we've got a vertical asymptote occurring there in the middle. It just goes up and up and up, which is exactly what calculus told me. I have 2 minimums. I do not have a maximum. Now, one thing that you will notice is that without writing it out, though, didn't we find all the intervals of increasing and decreasing when we did this process? So you could be asked to perform a problem, to answer a question where you're asked to find the critical numbers and then show the intervals of increasing and decreasing and also identify extrema. All of that could be asked in one problem. Just keep that in mind. All right, last problem. We have a graph here, and our question is, on what intervals is the function f increasing? And on what intervals is the function f decreasing? And at what values of x does f have any local extrema? But what I'm hoping you're seeing here is that this graph is not f. This graph is f prime. This is the derivative of f. So when I'm looking at this, I'm looking at the derivative. And so I'm going to use 2 things here. I'm going to use my pink highlighter for positive. I'm going to use my blue highlighter for negative. And the graph of this first derivative is positive here and positive here. The graph of the first derivative is negative here and negative here. Okay? The first derivative is equal to 0 here, here, and here. So if I were to write that out, what I'm saying is, on this pink interval, f prime is greater than 0. On the blue interval, f prime is less than 0. On the pink interval, f prime is greater than 0. And on the blue interval, f prime is less than 0. And at these 3 values, f prime is equal to 0. Now, in terms of calculus, that means that it looks like x equals 1, x equals 5, and x equals 7 would be critical numbers or critical values. And it looks like the intervals 0 to 1 and 5 to 7 are going to be increasing intervals for f of x. Now, how did that happen? The derivative is positive, the function's increasing. The original function, remember we're looking at f prime here, right? Same logic. What's happening from 1 to 5, and then again from 7 to what appears to be 8? it looks like we have a decreasing f of x on that interval, right? And then what's happening when x is 1? Well, to the left of 1, the function is increasing. To the right of 1, it's decreasing. It looks like we have a maximum of some sort there. What's happening at 5? Well, to the left of it, it's decreasing. To the right of it, it's increasing. So it looks like we have a minimum there. And then what's happening at 7? Well, to the left, it's pink. To the right, it's blue. To the left, it's increasing. To the right, it's decreasing. So it looks like increasing, decreasing. We have some sort of a maximum there. Now, you might be wondering, why did he put question marks here? Well, without having the original function f of x, I can't actually substitute these values in and be certain that that point is on the function. Okay? Now, it would be incredibly rare to find a function that had discontinuities at values, at these 3 values. But when you took the derivative was continuous at those 3 values, 1, 5, and 7. But it's possible. And if it's possible, then we have to say, well, if it's possible, I'm not certain that these are maxes and mins. Everything about this graph tells me to think that I probably got a max at x equals 1 and at x equals 7 and a min at x equals 5. But I'm not 100% certain. If I wanted to give a likelihood to it, I'd say I'm about 99% certain. If you could tell me that f of x is continuous on the closed interval 0 to 8, then I would say that those are absolutely maxes and mins. But lacking this, I'm not 100% certain, but I'm pretty certain. Okay? All right, this brings us to the end of section 4.3. Next section is section 4.4. See y'all back here for that.